Okay, greetings aspiring scientists. Welcome to another one of my videos. Today we're going to be talking mainly about concentrations and solutions, doing quite a lot of calculations. I do want to apologize for the lack of videos recently too. I try to do about one a week, but for the past 2 weeks it's been getting ready for IB exam season for the November exams, so a lot of rushing, trying to finish syllabus content and check students' final work, check IAs and EEs. I think I've had about 15 to check over the past week. And also students applying for university kept me really busy. But I did definitely want to make sure I get in a solid video this week. So we are going to be doing solutions and concentrations, and hopefully keep this under 1 hour. Okay, so let's go to my slides. Here we are, we're in structure 1.4.5, still in the unit of the moles, so counting particles by mass, the mole, but specifically the subunit solutions and concentrations, very much related to the idea of the mole as well. So there's some important vocabulary I think we must go over. First is solution. Most people know what this is, but especially if English is not your first language or you haven't done much scientific reading or study, you maybe don't really know the exact definition of this. So a solution is a homogeneous mixture of a solute dissolved in a solvent. Okay, those are going to be two of the next words I define. So just for now, realize that it's a solute dissolved in a solvent, something else. And we could have dilute means a little bit is dissolved in there. It's kind of a relative term. And then concentrated means a lot is dissolved in that solvent. Next, solute, something which is dissolved. Solvent, something which is used to dissolve. So you'll notice that I'm being pretty broad in general with these terms. I'm not saying that water is a solvent, or that a solvent is water, or that a solvent is liquid. Could be various things, but whatever it is, it provides the matrix and the excess surroundings. Next, aqueous solution. This specifically is a solution where water is the solvent. So water is in excess surrounding some particles of something that we dissolved in it, the solute. Concentration then, very specific definition. The amount of solute usually in moles per unit of volume, usually decimeter cubed. And we've learned from my unit or dimensional analysis video that 1 liter is the same as 1 decimeter cubed, so this is mole per liter as well. The basic unit of concentration. So you can see the equation I've written at the bottom here. Concentration written with a big C in units of mole per decimeter cubed equals amount of substance, N in moles, divided by volume of solution, V in decimeters cubed. Alright, so make sure you know all of these vocabulary words, because we're going to use all of them in today's video. So some other points. The concentration is sometimes called molarity. Molarity is the same as concentration, and it just means how many moles per decimeter cubed do we have of something. But molarity can be written with a big M. Instead of mole per decimeter cubed, you might just see a big M to mean molarity, and just realize that that means the same thing as mole per decimeters cubed. Similarly, you might see concentration instead of C or C subscript, you might see square brackets around something. And when the square brackets are around something, we're talking about the concentration of that thing. So on my slide here, I have the example square bracket A. That means the concentration in mole per decimeter cubed of A. So I'll try to mix in these different terms in my practice questions today, so you get some practice with all of them. You can use whichever you like, but you have to be able to read and understand all of them, I think. Alright, volumetric analysis. How are we actually going to go to the lab and start measuring fluids? Well, there's various ways with different levels of accuracy and precision and convenience. So starting with the left, graduated cylinder. These are for rough measurements when you don't really care too much about the volume. You can see they have single lines, usually per milliliter. And if you follow the rules of significant figures, this is an analog instrument, you can get one extra significant figure on these. But it just isn't very accurate in terms of even the volume that you would read on those lines. So what else can we use? Well, we can use a volumetric flask when we want to get exact measurements. These are really good for when you want to make a set volume of solution, and when that set volume is a very commonly needed number like 100 or 250 or 500 or 50 or 25 or 10, those kind of commonly used volumes to make a solution. But the thing is, they can only make that set amount. Okay, so I think I had it on my slide here that there should be a little circle. You can see it's a little gray circle moved to the right. But that little circle should be on the neck of that flask. And that means when you fill it up to that point, you know you have exactly the amount that's written on the front of the flask there. So it's written 100 milliliter. And if you fill it up to the line on the neck, you have added exactly 100 milliliters of liquid. Okay, so these are what we should make most solutions with. They're quite accurate, and they would have a low uncertainty for volume. But when you need to measure small amounts of not commonly used amounts, for example, like 22.7 or 1.63, we need to use other instruments that are capable of being adjusted. So we could use a volumetric pipette. This is what most high school labs would use, I think. They're quite cheap. It's just basically a glass tube, and it has a bunch of lines that indicate volumes. And what you do is attach some kind of suction power to the top. It might be like a rubber bulb or a plastic contraption that is like a vacuum pump when you squeeze it with your hand. But somehow you need to apply suction to the top and then stick the bottom of the volumetric pipette into your fluid that you're trying to extract. And you can carefully measure small volumes this way. It's much better than a graduated cylinder would be. So you might have 1 milliliter, 5 milliliter, 10 milliliter, 20 milliliter volumetric pipettes. What else? Micropipettes, so that's on the far right. These are quite a bit more expensive. They have disposable tips of plastic, so as soon as you're done transferring whatever liquid, you press a button and it shoots off into the trash can. They can measure very small amounts of volume. They're usually very well calibrated for like milliliters and microliters amounts, which is really handy. But they're probably going to cost quite a lot, hundreds or possibly $1,000. I don't really know. I haven't bought one in a while, but most high school labs don't really have them. Transfer pipette then. This is the cheapest one that are just mass produced in a factory. They're just for transferring non-measured amounts of liquid, basically. Sometimes there is a line on these that indicates 1 milliliter or 2 milliliters, but it is not accurate at all, so don't rely on that. Just use this if you want to like transfer a few drops of something and you don't care how much. Okay, all these images are generated by ChatGPT, but I think it did a pretty good job. A few lines are off here and there, but I think you get the general idea. So let's look at some calculations. There's going to be a lot today. So sample problem. Calculate the concentration in mole per decimeter cubed of a solution made with 0.663 grams of magnesium bromide MgBr2. This is an ionic salt which will dissolve easily in water. So it is completely dissolved in water to make a 100.0 milliliter solution. And then part B, calculate the concentration of bromide ions in the solution. Okay, so we're going to use some equations, one of them new today, but previously introduced in the moles section of my videos as well. Alright, let's go yellow. So what we would want to get is N, the number of moles of magnesium bromide, MgBr2. Do you guys remember what the formula for this is? It is mass of that divided by its molar mass in grams per mole, a value that you can get and calculate from the periodic table. So the mass that we had was 0.663 grams. The molar mass, you would have to go find magnesium and 2 bromines. So magnesium, I think, is 24.31. And bromine, 2 of those at 79.90 each. Okay, and these will be in units of gram per mole on the bottom. Okay, so you should get that the mass of MgBr2 is 184.11 roughly. So when we divide, we'll multiply by the reciprocal of these units, cancel out grams, and we'll get 0.0036. And I'm just going to include a couple more significant figures for now before we reach the answer. 3601 mole. Alright. So that's just how many moles we have, but we need a concentration in mole per decimeter cubed. So we'll use the new equation. Concentration equals moles per unit volume. 0.00361 mole per. So 100 milliliters, that's 100 centimeters cubed, that's 0.1000 decimeter cubed. And so we will get 0.036. And now this will be the final answer, so let's think about significant figures. We shouldn't really write more than 3 because of our 0.663 grams only having 3. So let's leave it at this. 0.0360 mole per decimeter cubed. Final answer. Alright, part B, calculate the concentration of bromide ions in the solution. So what's the difference between part B and part A? Part A was we found the concentration of MgBr2. But there is a ratio of MgBr2 to single Br. Or you could ask the question, how many Brs exist inside of an MgBr2, or if MgBr2 was broken down and dissolved, how many Brs could be released? So that ratio is 1 to 2. And that means the number of moles of Br is simply double the number of moles of MgBr2. So 0.00720 roughly. And that amount will also be divided by the same volume. We're still in a 100 milliliter solution. You don't have to do these first 2 steps, actually. You can just jump right to the concentration, because the concentration will be just double that of MgBr2, but I'm just showing some smaller steps for anyone who needs them so that they can follow. So the concentration of Br is equal to that number of moles, 0.00720 mole, divided by 0.100 decimeter cubed. 0.0720 mole per decimeter cubed. Final answer for part B. Okay, and it should be exactly double the concentration of MgBr2. And that's all because one molecule of MgBr2, not really molecule, but a ionic unit, dissolves and releases 2 particles of Br. That's why. Okay, let's move on. I think I have some more practice. Calculate the mass of sodium acetate, NaCH3COO, in 275 centimeters cubed of a 1.25 m, remember that's mole per decimeter cubed, same units, solution. Okay, so how are we going to do this? It's a bit different. But again, you have a volume, 275 centimeters cubed, and a concentration, and we can use today's equation. Oh, sorry, let me go back. Switch to pen. C equals N over V. Amount in moles divided by volume. But I think what we would like to know first is how many moles would be in this solution. So we don't have too many things going on here. I'm not going to label every subscript, but the number of moles we can understand means sodium acetate. So this is C multiplied by V, 1.25 mole per decimeter cubed. Multiplied by 0.275 decimeter cubed. Don't forget to convert this properly into units that will cancel out properly, like this. So that should come out to 0.3438 roughly. I'll keep a bunch of significant figures. So that's how many moles would be in this solution. So if we were going to make this solution, we would want to know how many grams, right? The mass. And that's really what this question is asking us. So we had an equation from the moles unit previously. Number of moles equals mass over molar mass. Little m over big M. But in this case, I'd like to know the mass. So the mass is the number of moles times the molar mass, like this. So I can use the moles I just calculated above, 3438, and multiply by the molar mass. This molar mass is going to be quite large. It's a lot of things going on. NaCH3COO. Alright, so that's 22.99 for Na. One of those. Then CH3COO, that's 2 carbons. They're 12.01 each. What else? Hydrogen, we've got 3 of them. CH3, 1.01. And finally oxygen, 2 of those. They're 16 each, mass units. Okay, so all that, and these have units of gram per mole. I'm just going to write it once. So if you just punch those all in your calculator, very carefully not to miss any digits or put a decimal place in the wrong spot. Alright, I think you'll get that the molar mass on the right there is about 82.04. Multiply it by 0.3438. Should get 28.205 roughly, and then we'll think about significant figures to report this final answer. We really should not have any more than 3, so I can just easily round this to 28.2 grams of sodium acetate. Final answer. Okay, hopefully you follow that. So it's a kind of the opposite pathway to the previous question, but sometimes you'll be asked how much mass would it take to make a certain concentration of something in a certain volume. Okay, moving on. We need to discuss a little bit about how dissolving affects acids and salts. We really haven't talked about what these are chemically yet in my videos, but we are talking about solutions right now, and we just have to know some things, so let's learn it now. So dissolving many compounds in water causes them to separate into ions. You guys know what ions are. It's when an atom or polyatomic group of things loses or gains electrons to become cations positive, anions negative. So dissolving things in water often will separate these, especially salts and acids. So for example, a salt, NaCl, sodium chloride, that you put on your food as salt, this will separate into its components, Na and Cl. However, these elements will tend to arrange their orbitals and their electron configurations into noble gas configurations. Okay, if you need more review on that, go watch my video on electron configurations, but in that video, I mentioned that it's much more stable when atoms have a full shell resembling a noble gas configuration. So when Na and Cl separate, the Cl is going to take one of the electrons from sodium. That way the Cl gets a full noble gas configuration of 8 valence electrons, and the Na will go down to the most recent noble gas configuration as well. More stable that way for both of them. And so that means the equation I have here at the bottom, NaCl solid dissolved in water, that's what H2O above this arrow means, goes to Na plus aqueous, meaning dissolved, now dissolved state, plus Cl minus, chloride anion, also aqueous. Okay, so you've got to get used to this. It's not only going to be NaCl, but any salts, which will usually have metal and non-metal, things like, I don't know, lithium bromide or magnesium hydroxide, these kind of things, separate into cations and anions. So salts separate into cations and anions. What about acids? Acids are going to split into H+, hydrogen cation. And something else, probably another anion, although it doesn't have to be. So here's an example, H2SO4, sulfuric acid. I have an arrow that should have a water on the top, showing dissolving in water, but this will dissociate, separate into 2 H pluses and 1 SO4 2 minus, the sulfate polyatomic anion. Okay, so try to get used to predicting how these things go. You're not going to be told every time. It's something that you need to realize yourself. Alright, more practice. Calculate the mass of nitric acid, HNO3, required to prepare 500 centimeters cubed of a 2 mole per decimeter cubed H plus solution. Alright, let's do that. So first of all, we need to make an H plus solution, but we're working with HNO3. That's what we're told. We need to measure the mass and then input into our solution. So first, let's analyze this. What's the ratio of moles of HNO3 to H plus? If it were to dissociate in water, like I showed on the previous slide, HNO3 in H2O goes to H plus NO3 minus. Even if you don't know what goes on the right here, this NO3 minus, you should realize that one molecule of HNO3 can release and will release one molecule or one cation of H plus. So the ratio here must be 1 to 1, and that's very handy. That means we just have to find the mass of HNO3 that would be required. And then the mass of, the mass of HNO3 to make this concentration will also make the same concentration of H+. We can say that for sure. Alright, so what's next? I think we'll use C equals N over V. And we want to know the moles of HNO3 required. So this is going to be C times V which are provided in the question, 2.0 mole per decimeter cubed. And we have a volume here of half a liter, 500 centimeters cubed, 500 milliliters, that's 0.500 decimeter cubed. Should be pretty obvious. This is going to come out to 1.00 mole. I was going to write per decimeter cube, but this is just moles. So 1 mole of HNO3. This will provide a 2 mole per decimeter cubed solution of HNO3 and of H+ as well, because they have a 1-to-1 ratio when they separate. Okay, not quite done yet though. This asks what mass would that be. So again, we'll use number of moles equals mass over molar mass, but we want the mass this time. So number of moles times molar mass. We're using exactly 1.00 mole. And then what is the molar mass of HNO3? That's going to be 1.01 for the hydrogen. How about nitrogen? That's 14.01. And then 3 oxygens, 3 times 16. And reminder, all of these have units of gram per mole. So we'll cancel out our mole units and be left with a mass. Just again, be careful putting that in your calculator. But you should get 63.02 grams. We should really only have 2 significant figures here though. We have a 2.0 mole per decimeter cubed in our starting values. So we'll just keep it to 63 grams. Final answer. Okay, let's go dilutions. Hopefully you guys know what this means. It means taking something that's concentrated or a lot of stuff in a small space and spreading it out, adding more solvent. So imagine transferring a volume of solution into a new container and mixing with a different volume of solvent. So some things we have to realize about this situation. We are not adding any more solute. Whatever was there at the beginning is going to be there at the end. And this is an important idea I've written in the top right. N1 equals N2. Okay, the number of moles of solute that we're talking about stays the same in the initial situation to the final situation. Number of moles initial, number of moles 1 equals number of moles final, N2. This must be true. There's conservation of matter. We're assuming we have a closed system here in our containers. So then you can write this line I have in the middle. Number of moles for situation 1 equals CV, C1V1 for initial conditions. But all of that equals N2, so this must also equal C2V2, the final conditions. So I'm just going to focus right on the center section of that. This is what you're going to use to solve most questions. C1V1 equals C2V2. Just say that 10 times, and hopefully you'll remember it. It's got a nice ring to it. It's not in the data book, so if you want to use it, you have to realize that the actual situation is N equals N. Okay, number of moles has not changed, and so C1V1 equals C2V2. Specifically, what are each of these? C1, concentration of original solution. V1, volume of original solution taken. C2, final desired concentration. And V2, final desired volume. Okay, it's very important to pick out the right values for each of these variables. We'll go through some sample problems. And then just one more thing I want to mention on the right side. Oftentimes, you might rearrange this for C1 or V1. So C1 equals C2 times V2 over V1. And you'll notice there we have a ratio of volumes, V2 over V1, so those units will cancel out, and they'll just provide a ratio number that we'll call the dilution factor. And it sort of modifies the final concentration, C2, and tells you how you would get C1, or vice versa. And so we call that the dilution factor. You'll often hear people say, oh, I want to dilute this by 10 times or 100 times or 1,000 times. What they're talking about is that dilution factor there. So in this case, usually V2 is much larger than V1. So that dilution factor usually would come out to be like 100 or something, or 1,000, depending on how much we're diluting. And then an important thing I want us to know is that the remaining volume of that final container will be filled up with solvent. Okay, we're not just leaving it empty. We're filling it up with solvent for this dilution to make any sense physically. Okay, let's check. Dilution practice. A standard solution is prepared by dissolving 6.45 grams of sodium sulfate, Na2SO4, in a 100 centimeter cubed of distilled water in a volumetric flask. At 5 centimeters cubed, sample is then removed by volumetric pipette and diluted with water to a final volume of 0.250 decimeters cubed. Calculate the concentration of the distilled or the diluted solution. Okay, so how are we going to do this? Well, I think we can clearly find a number of moles here of sodium sulfate. Sorry, let me go pen. So number of moles equals mass over molar mass. Same thing as usual. 6.45 grams. Molar mass of this is going to be pretty huge too. We're going to have 2 sodiums, 2 times 22.99. What else? Sulfur, 32.07, one of those. And then 4 oxygens, 4 times 16. Okay, so 6.45 grams divided by this many gram per mole. Put it all in your calculator carefully. So on the bottom there, we should get about 142.05, and then dividing these two numbers, we should get 0.0454 moles. All right. Now, what's the concentration going to be? N over V. Always N over V. So that number of moles that we just calculated divided by the volume of the first container. I'm still looking mainly at the first line of this question. So that's 100 centimeters cubed. That's, 0.1 decimeter cubed. And so we get 0.454 mole per decimeter cubed. Okay, now we need to do our dilution. C1V1 equals C2V2. So we did that whole calculation on the right side to determine what C1 is, our initial concentration. Now it says we're going to take 5 centimeters cubed of that. We're trying to make a new solution which will be diluted with water up to 250 centimeters cubed, or 0.250 decimeters cubed. So calculate the concentration of the diluted solution. That's our final situation after doing work on this. That's going to be C2. So this equals C1V1 over V2, rearranging this equation. Okay, put the numbers in, 0.454. It says we take 5 centimeters cubed. That's 0.005 decimeter cubed. And V2 we're trying to make 0.250 decimeter cubed solution. Okay, this comes out to be 0.00908 mole per decimeter cubed. Fairly dilute solution, but that's final answer done. Okay, so work with what you have to get those C1s and V1s and C2s and V2s as much as possible. You'll need to have at least 3 to calculate the final unknown usually. But notice how we don't use that initial volume, 100 centimeters cubed, after we've used it to calculate C1, the initial concentration, right? All of this on the right side was to get our C1. Okay, moving on. Okay, more practice. A standard solution was prepared by dissolving 6.93 grams of sodium carbonate, Na2CO3, in deionized water using a 500 centimeter cube volumetric flask. Calculate the volume of this that should be taken with a micropipette to make a new 0.00100 mole per decimeter cube solution in a 100 centimeter cube volumetric flask. Alright, again, let's figure out the number of moles we're working with at the start here. N equals mass over molar mass, 6.93 grams. Over everything in this, so 2 times sodium's 22.99. 1 carbon. And 3 oxygens. So that should come out to 0.0654. moles, roughly. Alright, then what? Then what would the concentration of the solution made be? N over V, always N over V. We're in 500 centimeters cubed this time. That's 0.5 decimeters cubed. So this will come out to about 0.131 mole per decimeter cubed. Okay, and then we'll do our dilution. I'll just make a little area over here for this. So C1 V1 equals C2 V2. This time though, we're not looking for the final concentration. We're looking for how much should be taken with a micropipette to make a new solution. So in this case, we're looking for V1. That's C2 V2 over C1. Rearranging this. So our final concentration needs to be 0.001. Our final volume, V2, is 100 centimeters cubed. That's 0.100 decimeter cubed. And our initial concentration, that's what we did all the work for over here to find C1. That's 0.131 mole per decimeter cubed. So in the end, what do we get? We get 0.000763 roughly decimeters cubed. I'd write that in scientific notation actually. It's too many zeros, but I'm out of space here, so let's leave it at that. Final answer. And we should have 3 significant figures. So 0.000763 decimeters cubed. That's how much we'll transfer. We'll have to probably use a micropipette. As it says, it's a small amount. Alright, good practice. Let's move on. So that brings us to something called titration. Very important technique and something you'll often see on exams and in your practical work. If you have a textbook, go look at the definition in that textbook, but I'm going to use the IUPAC Gold Book definition. I forgot to write that here, but I got this from there. Not trying to plagiarize. Okay, the process of determining the quantity of substance A by adding measured increments of substance B, with which it reacts, almost always as a standardized solution called the titrant, but also by electrolytic generation, as in coulometric titration. Okay, a lot of crazy words there, but basically it means we're going to be mixing 2 things together. One of them we know the concentration of, the other we don't, but there's going to be some kind of interaction, in our case in chemistry, a chemical reaction probably. And we need some provision for some means of recognizing or indicating the end point, at which essentially all of A has reacted. So we're going to be adding these things together slowly, and what we're looking for is something called the end point, where the reaction is done. Alright, if the endpoint coincides with the addition of the exact chemical equivalents, it is called the equivalence point, or stoichiometric or theoretical endpoint, thus allowing the right amount of A to be found from known amounts of B added up to this point. The reacting weight ratio of A to B being known from stoichiometry or otherwise. So this is important for titration to be of any use. We basically need to know a balanced chemical equation or mole ratio. And if we do know that, we can set up our titration and check for the endpoint. Okay, terms for varieties of titration can reflect the nature of the reaction between A and B. Thus, there are acid-base, complexometric, chelatometric, oxidation reduction, and precipitation titrations. Tongue twisters there. Just various types of reactions that we can put in here. Most of the time, we're going to see acid-base, honestly, in beginner level here, maybe some reduction oxidation. That's about it. And this note I have at the bottom, indication is often done by a colored indicator. So you might have heard of things like phenolphthalein or methyl blue, methylene blue, methyl orange. Even starch and iodine can be used to color these things so that you can clearly see when the endpoint happens. Okay, moving on. Let's see a diagram of a titration. This is how it will usually be set up. A burette attached to some kind of clamp or holder filled with our titrant liquid. And we're going to be dropping that drop by drop into a flask underneath, usually a conical Erlenmeyer flask, which holds our analyte. That's our thing that we're combining the titrant with to do the reaction. Alright, so it's easy to look at this picture, but until you go to the lab and set this up yourself, you probably don't really have a good idea of what it takes to set this up correctly. So at the bottom of the burette there, you have the stopcock. This will control how fast the flow rate flows through. You want to get it to about, I don't know, a slow flow rate of like drip, 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 and even slower than that when you think you're reaching the endpoint. So if you have an indicator in the analyte, you'll see some color change, but it will disappear unless you're at or beyond the endpoint. So it takes some skill to get near there carefully and not go over. So let's look at how the calculation for this might go. Calculate the volume in decimeters cubed of 0.276 mole per decimeter cubed LiOH solution that will neutralize 37.0 centimeters cubed of 0.330 mole per decimeter cubed phosphoric acid, H3PO4. And then this question nicely provides us with the balanced chemical equation. 3 LiOH reacts with 1 H3PO4, and that will make water and Li3PO4. And I think this should be, 3 water. That's not really important for this calculation, but, just balance the equation properly anyway. Okay, so what are we going to do? We need to first work with what we have. We have a concentration and a volume of phosphoric acid. So let's just find out how many moles would be in there. Okay, let's just call it pH, phosphoric acid, equals C times V, 0.330 mole per decimeter cubed times V, 37 centimeters cubed, that is 0.0370 decimeter cubed. Alright, so put those in the calculator. We should get 0.01221 roughly moles of phosphoric acid. Now the question is, what's the volume of the lithium hydroxide, LiOH, that will be needed to fully neutralize this? So that means just fully react with it and complete this balanced chemical equation fully. Well, what's the ratio here of phosphoric acid moles to LiOH moles? You can look at the equation right above it. To eliminate 1 H3PO4, it requires 3 LiOHs to do that every time. So this ratio is essentially 1 to 3. So that means if we have what we have on the right here, 0.01221 moles, we're going to need triple that when it comes to LiOH. Triple the phosphoric acid moles. And so that comes out to 0.03663. That's good. And we know the concentration of this LiOH solution, so you can then find a volume. Remember, C always equals N over V, so V equals N over C. You can switch the places of C and V there through a rearrangement. We'll put in the moles of LiOH, 0.03663, divided by the concentration we were given in the question, 0.276 mole per decimeter cubed. Okay, put that in the calculator carefully. This comes out to about 0.1327 decimeters cubed, and we should keep about 3 significant figures. That's what we had in the starting materials, so 0.133 decimeter cubed. I'll put that as my final answer here. So that's quite a lot. It's 133 milliliters. That's probably going to be several burettes worth. So this person might consider making even higher concentration LiOH to do this titration a little bit quicker. But that's basically what the titration calculations will usually be like. You might be thrown something new here or there, but they'll follow this basic structure. Okay, let's move on. Another quick thing I want to go through is mass concentration rho. Okay, this is not a P, this is Greek letter rho. So sometimes concentration can be expressed directly as a mass per unit volume, for example, gram per decimeter cubed instead of mole per decimeter cubed. You'll often see this in biology or other types of science other than chemistry. But what are we doing here? Well, this can, first of all, cause you problems later. In chemistry, we often need moles, right? So it's not actually that helpful just to have grams per decimeter cubed. So this may cause you problems when you need moles instead, so consider when to use this. Your equations should be written as in the following example. So rho of something as a subscript usually. I'm just using NaCl as an example. So rho, mass concentration NaCl, equals mass of solute divided by volume of water, or whatever the solvent is. Mass in grams, volume in decimeters cubed. So very similar to moles, it's just we use mass instead. But there's a cool trick to quickly convert between concentration and mass concentration. So concentration C and mass concentration rho can be changed directly through the molar mass, and this relationship exists. Concentration equals rho over m, where rho is the mass concentration and big M is the molar mass. So we'll have gram per decimeter cubed divided by gram per mole. That will give us the units that we require, mole per decimeter cubed, for concentration. Okay, so let's look at a practice question. Calculate the molar concentration of sodium bromide in mole per decimeter cubed in a solution prepared by dissolving 2.22 grams of NaBr, that's sodium bromide, in water to make 25.0 centimeters cubed of the final solution. Then calculate the mass concentration, rho. Okay, so what are we doing here? First, just concentration as normal. Oh, sorry, pen. Concentration equals mole per volume. But we actually need moles first. So moles equals mass over molar mass, 2.22 gram, divided by 22.99 for sodium, and 79.90 for bromine, and we should get 0.02158 mole. Okay, and going back to concentration here, 0.02158 mole per. Our volume here is 25 centimeters cubed, that's 0.0250 decimeter cubed. So we'll get 0.8631 mole per decimeter cubed. And this does have to be a final answer to this question, so let's just round this to our three significant figures, 0.863. Okay, that's the first part. And then we can do the mass concentration. So concentration equals rho, the mass concentration over the molar mass. That's what I showed on the previous slide. And we want rho, so rho equals, rho equals C times M, 0.863 multiplied by m again. Previously I calculated 22.99 times plus 79.90. That was 102.89 gram per mole for sodium bromide. So you can see those units will cancel nicely. Mole disappears. We'll be left with gram per decimeter cubed, and that is the units of mass concentration. So this is 88.8 roughly gram per decimeter cubed. Final answer done. Seems pretty high, but salts can usually dissolve very well in water. Okay, we're almost done. This video is too long, but I just want to introduce one real-world application of this, making solutions. When would we do this a lot? So similar to if you buy juice or coffee concentrates from the supermarket where you can just dilute a little bit in water and make a nice drink, chemists often prefer to buy concentrate solutions as well and then dilute it for daily activities. So this is called a stock solution, the concentrated one that we buy usually from a company. When the concentration is well known, for example, when you buy it from a trusted chemical company, it's called a standard solution. So stock solutions and standard solutions, very useful and convenient one-time purchases to make very many small solutions. Now, we often want to know the concentration of a certain chemical in unknown solutions. Okay, maybe I want to go take a sample from the river or the ocean or the soil or something, and I just want to know how much of some chemical is in there, what kind of concentration. One of the most common methods to do this is called spectrophotometry, measuring through light. That's literally what this means. Measuring visible light specifically is called colorimetry, so in the visible part of the spectrum. One important relationship here is Beer's law. This is actually not really part of the IB chemistry curriculum, but it's part of most university curriculums. I'm sure you'll see this if you take chemistry in university. So Beer's law says concentration is proportional to absorbance of light. So if you have something that absorbs light in your solution dissolved, the amount that it absorbs is directly proportional to its concentration amount. So if you have some amount with some absorbance, if you double that concentration, you'll double that absorbance as well. So this is shown through Beer's law equation. Absorbance A equals epsilon Cl, where epsilon is something called the extinction coefficient. It's just a property of your chemical, your solute dissolved in the solvent. C then is the concentration of that solute in the solvent. L is the path length. That's just how wide your container is that you're passing light through to check the absorbance. So I have a little model here made by Cloud AI. You have a light source. It has 100 intensity. Then you have your solution in a container with a path length. In this case, it's 1 centimeter. And then a detector. This detector will detect the light that has passed through your sample. In my example here, it's 0. That means our solution here has 100 absorbance or 100% light absorbed, so nothing gets through. But the general formula and the true meaning of absorbance depends on these two intensities of light from the source and at the detector. So it's 1 minus I divided by IO. Okay, you can imagine these as percentages here. So if I have 23% of light transmitted through there, maybe my detector measures 23, then my absorbance is 100% minus that, or 1 minus that fraction. So it would be like, what did I say, 23? That would be 77 absorbance. Okay, you don't really have to know that, but it's good to understand how the instruments work. I had some students use these instruments for IAs before. So UV-Vis spectrophotometer. I asked ChatGPT, I think, to make an image for me. And this is what it came up with. Just let me point that out. This is not a real one. This is ChatGPT generated. But essentially it will be like this. You have a place to put in your sample, a place to put in a reference. The reference will usually be just diluted or distilled water, so it shouldn't really be blue in this picture. But you always want to be comparing against a blank sample, something that's set to 0. So the instrument here can measure either the transmittance, how much was allowed through, or the absorbance, which is 100 minus the transmittance, 100% minus that transmittance percentage. So they are opposites of each other, and this will be done for ultraviolet and visible light in a UV-vis spectrophotometer. However, due to constant systematic errors in these devices, this must be calibrated often, preferably daily. I used to have a job where I did this almost every day. So what does it mean to calibrate this? It's actually quite a process that involves a lot of the things we discussed today. So what you would do is make a series of solutions that can provide you with a curve. Well, really it's a straight line, but we call it a calibration curve. So you can see on the left here, maybe I'm making some potassium permanganate solutions, and I'll make them in series from very concentrated on the left to slightly in the middle, and then approaching 0 on the right. And for the 0 point, I will make actually distilled water, no potassium permanganate in there. And then I'll put these in the instrument and measure how much absorbance each has. So my blank water should have essentially 0 absorbance. I should also mention this is measuring at one specific wavelength. This is 683 nanometers in the kind of red zone. But you do have to set a specific wavelength range for this to kind of work properly. So we get what looks basically like a line here, these 5 points from my 4 permanganate solutions plus blank water. And then your software basically should be able to create a line of best fit for this and provide a linear graph with a slope. But just looking at this, you could try to answer the question I have on this slide. An unknown solution of potassium permanganate has an absorbance of 0.285 on this instrument on this day. What's its concentration? Well, just looking at our calibration curve for this day, 0.285 is around here, so bam, it's going to hit our straight line of best fit around there somewhere, so about 0.35 mole per decimeters cubed, we could say. So that's how a basic instrument like this works and how you would calibrate it every day. You have to prepare these concentrated solutions, which are 0.1, 0.2, 0.3, 0.4 mole per decimeter cubed. That's what all these points represent. A lot of IB exams ask you, like, how would you physically prepare these 4 solutions? And you'd have to go through making, the most concentrated one first, then diluting it one by one to get these other 3 solutions. All right. So I think we'll stop there for today. That's all about concentrations and solutions. A lot of practice questions and calculations, but hopefully you learned something. Thanks a lot, guys. See you in the next one.